Today we will be doing chemical equilibrium. See, in chemistry, you all know about reversible reactions. So, in a reversible reaction, basically what happens is that the forward reaction and backward reaction proceed simultaneously at different rates. And there is one law according to which the rate of the reaction suppose we want the rate of the forward reaction, so it is Kf into concentration of A to the power A into concentration of B to the power B. Kf is called rate constant of forward reaction. Similarly, so this is the rate of the forward reaction. Then rate of the backward reaction is so this is Kb. Kb is the rate for constant of the backward reaction. Now what happens is that as the reaction proceeds, it reaches a stage known as chemical equilibrium. So at chemical equilibrium, the rate of forward reaction is equal to rate of backward reaction. So the rate constant of forward divided by rate constant of backward reaction is equal to this particular term. Now the thing is that these quantities enclosed in third bracket, they are called active mass, and active mass for all practical purposes, it means molar concentration. So this particular expression is called the equilibrium constant of the reaction. So the equilibrium constant of the reaction is denoted by Kc, that is concentration of C to the power small c into concentration of D to the power small d divided by concentration of A to the power small a into concentration of B to the power small b. So this is known as the equilibrium constant of the reaction. Now, one important thing is that when the reaction reaches chemical equilibrium, the rate of forward reaction is equal to the rate of backward reaction, which basically means that the concentrations of the reactants and products, it becomes constant thereafter. Like after that, the concentrations of reactants and products does not change. And another very important thing, this equilibrium constant, it depends only on the temperature. So the dependence of rate constant on temperature is a study of chemical kinetics, which is a different chapter. So if temperature is constant, then the rate constant of or equilibrium constant of a reaction will also be constant. Now, suppose there is a reaction in which the reactants and products are all gases. So capital A, capital B, capital C, capital D are all gases. So in that case, we choose a different equilibrium constant. So this is known as Kp. Why? Because in this case we will not use molar concentration, we will use partial pressure. So Pc is the partial pressure with respect to C, Pd is the partial pressure with respect to D, Pa is the partial pressure with respect to A, and Pb is the partial pressure with respect to B. So the equilibrium constant is designated as Kp. Now you have to remember that all the reactants and products are gases, in which case we can apply the gas law PV equal to nRT. So P is N by V into RT. So suppose if I am writing partial pressure due to C, then it will be molar concentration of C into RT. Similarly, partial pressure due to D will be molar concentration of D into RT. Partial pressure due to A will be concentration of A into RT. Partial pressure due to B will be concentration of B into RT. So after making all these changes, the expression becomes like this. So we can now write it in this form. So this is equal to Kc into RT to the power delta N, where delta N is the difference in number of moles of products minus reactants, right? Delta N is equal to the difference in number of moles of products minus reactant, and Kc of course is the equilibrium constant using molar mass concentration of all the reactants and products. So this is the equilibrium constant if all the reactants and products are gases. Now, suppose there is a reversible reaction which has not yet reached chemical equilibrium. So, in that case, what will happen is that this ratio is known as reaction quotient, and it is denoted by QC. So this is the reversible reaction, and this particular expression, which at equilibrium is called equilibrium constant. So at any intermediate situation, it is known as reaction quotient. So this is the reaction quotient. Now the thing is that if reaction quotient is less than equilibrium constant, it means that the denominator is greater than expected and numerator is less than expected, so the reaction will proceed forward. If the reaction quotient is greater than equilibrium constant, it means that the numerator is greater than expected and denominator is lesser than expected. So the reaction proceeds backward. So if QC is less than Kc, reaction proceeds forward. If QC is greater than Kc, reaction proceeds backward. And if QC is equal to Kc, that means the reaction is at chemical equilibrium. Now, there are some very well-known reactions, reversible reactions, and they are this H2 plus I2 is 2HI. PCl5 is PCl3 plus Cl2. N2O4 is 2NO2. N2 plus 3H2 is 2NH3. Two SO2 plus O2 is equal to 2SO3. So these are some very well-known reversible reactions. Now let's have a look at, for analysis purpose, let's have a look at these reactions, this one, and this one, and these two reactions you can analyze it as a homework. Now let us analyze these three reactions, these three, and these two you can practice it at home. First, let us analyze H2 plus I2 equal to 2HI. So let the initial concentration of H2 be A, let the initial concentration of I2 be B, and 2HI is 0. When chemical equilibrium is reached, then the concentration of this becomes A minus X, this is B minus X, and this is 2X. So the equilibrium constant so equilibrium constant is 4x square by A minus X into B minus X. Now, in this expression, first of all, we can say one thing, that if A and B increase, then X must increase. Okay, that is the first conclusion that we can make, that if A and B increases, after all temperature is constant, so Kc should be constant, so that means X must also increase. Secondly, there is no volume term in this fraction, so if pressure changes, then there is no change in the progress of the reaction, because only when there is a volume term in this expression, then change in pressure will affect the progress of the reaction. Number 3, if inert gas is introduced, then also there will be no change, because there is no volume term, and secondly, inert gas will not react with any of these, so in any case it cannot affect the equilibrium from the reaction point of view, but because there is no volume term, inert gas will not cause any change in the progress of the reaction. So this is the analysis of the reaction H2 plus I2 equal to 2HI. So now we will analyze this reaction PCl5 equal to PCl3 plus Cl2. So suppose concentration of PCl5 is A, concentration of PCl3 and Cl2 is 0, and at equilibrium this is A minus X, X and X. So Kc will be X by V into X by V divided by A minus X by V. So it is coming X square by V into A minus X. Now once again let us do the analysis. First of all, if A increases, then X must increase. If A increases, then to keep Kc constant, X must also increase. Secondly, if pressure increases, now see, if pressure increases, then volume will decrease. If volume decreases, to keep Kc constant, X will decrease. Third point is, if you introduce an inert gas, so if inert gas is introduced at constant volume, then there is no change. Now suppose inert gas is introduced at constant pressure. So if inert gas is introduced at constant pressure, then what will happen? The volume increases, therefore X also increases. So if inert gas is introduced at constant pressure, the volume increases and therefore X also increases. So this is the analysis of PCl5 is equal to PCl3 plus Cl2. Now let us analyze the Haber's process, N2 plus 3H2 equal to 2NH3. So as usual, initial concentrations are A, B and 0, and at equilibrium the concentrations are A minus X, B minus 3X and 2X. So Kc is 2x by V whole square. So this is B minus 3x by V whole cube. So this is the expression for Kc. Again, let's do the analysis. If A and B increase, then X must increase. So this is the first thing that we can say, that if A and B increase, then X must increase. Secondly, if pressure increases, then volume decreases, so X will increase. So once again, if the pressure increases, that means volume decreases. So to keep Kc constant, X will increase. And third point, if inert gas is introduced at constant volume, then there is no change. And if inert gas is introduced at constant pressure, now you know that if inert gas is introduced at constant pressure, you know that volume will increase. So that means X will decrease. So these are the various points of analysis of the Haber's process. Now there is another qualitative analysis of all these reactions that is known as Le Chatelier's principle. So Le Chatelier's principle is basically a method by which we can qualitatively analyze a reaction. So it states that if a change is introduced into a reversible reaction at equilibrium, then the reaction will proceed in a manner so as to oppose the change. So if you try to force a change on this equation, the equation will respond by proceeding in such a direction as to oppose the change which you are trying to introduce. That is known as Le Chatelier's principle. Now, to begin with, first let us talk about concentration of reactants. Now what happens is that N2 plus 3H2 equal to 2NH3. If you change the concentration, or rather if you increase the concentration of any of the reactants, suppose if you increase the concentration of these two reactants, then what will happen is that the reaction will try to oppose the change. So it will try to lessen the increase in concentration, so it will proceed forward. So first point is, if you try to increase the concentration of the reactants, the reaction will oppose by proceeding forward. Second is increase of pressure. Suppose we try to increase the pressure in this reaction. Now you will understand that all these are gases, and therefore we can measure the partial pressure due to each gas, and as you know, partial pressure is proportional to mole fraction. So the number of moles on the left is 4 and number of moles on the right is 2. So if you try to increase the pressure, the reaction will try to oppose you by proceeding in a manner so as to decrease the pressure, which means it will proceed to the right because there are lesser number of moles on the right. So point number 2, if you try to increase the pressure, the reaction will oppose you by proceeding in the direction where there is lesser number of moles. Point number 3, increase of temperature. Now, Haber's process is an exothermic reaction. If you try to increase the temperature, you know that according to Le Chatelier's principle, the reaction will try to oppose the increase of temperature. Increase of temperature causes liberation of heat, so the reaction will oppose the increase of temperature by absorbing the extra heat. So that means increase of temperature will cause the reaction to proceed in the direction of absorption of heat. Now this is an exothermic reaction, so this is the direction of liberation of heat, so the opposite will be the direction of absorption of heat. That means in this particular reaction, if you increase the temperature, it will go backwards, right? So once again, Haber's process is an exothermic reaction, and whenever you increase the temperature, the system will oppose you by going in the direction of absorption of heat. So in this reaction, if you increase the temperature, the reaction will proceed backwards because that is the direction of absorption of heat. Number 4, number 4 is introduction of catalyst. Okay, if you introduce a catalyst, actually what does a catalyst do? It accelerates the reaction. Now there are two reactions, forward and backward. If you introduce a catalyst, it will accelerate the forward and backward reactions equally. So the net result is that the state of equilibrium will not change, but the equilibrium will be achieved faster. Once again, if you introduce a catalyst, it will accelerate the forward and backward reactions equally. So the state of equilibrium will not change, but the equilibrium will be achieved faster. If you introduce an inert gas at constant pressure, then what will happen is that at constant pressure the volume will increase, so as a result the molar concentrations will decrease. So if you introduce an inert gas at constant pressure, the volume will increase. That means the molar concentrations will decrease. So the reaction will try to oppose the change by trying to increase the molar concentration, which means that the reaction will proceed in the direction where there is greater number of moles. So if you introduce an inert gas at constant pressure, the reaction will proceed towards that direction where there is greater number of moles. Suppose if you introduce an inert gas at constant volume, so you know that if you introduce an inert gas at constant volume, then in that case the molar concentrations will remain unchanged. So that means that the progress of the reaction will be unchanged. So that completes Le Chatelier's principle, and it also brings us to an end of this session of chemical equilibrium.